Hello. I want to talk today about another example of procedural teaching and how what I try to do with my practice is to move away from it. It comes from a philosophy that I think is important in science, and that is to make sure that the pupils understand how the device in which they're using to process some sort of question, be it numerical or whatever, that device is understood, how it works is understood, and so therefore how the answer was gained is understood. Now sometimes, and I've spoken to quite a few maths teachers about this, the idea that something needs to be conceptually taught is something that some maths teachers say, well, perhaps the method that suits them best is to prove a procedure once, and then to use the procedure without ever questioning it again. And so once you've gained a methodology, is just to apply that methodology in each instance. Now I think that is fine, and I think that that does work for certain mathematical situations. It also works in the real world, because let's face it, if you want an answer, you'd probably just look it up without working towards the answer every single time. But I think physics is different. I think what we're trying to bring out of the pupils is the skill of the demonstration of how you got that answer. It's every physics teacher's favourite hobby to write "show you're working." But what if a particular methodology is used that is a black box that the pupil, for example, cannot see inside? Now, a familiar example to us of this is the formula triangle. Now, the formula triangle you may have seen looks something like this. You've got the distance divided by time gives you speed. And so how the formula triangle works is a pupil unable to remember the relationship that distance divided by time gives speed, or to understand what that means, would take the numbers, identify which quantity is which from the units, and then blindly put it into this formula triangle. Now, it's not always the case that they blindly put it into the formula triangle. Some people understand what the formula triangle is doing, but choose to use it because it's a nice memory aid for the relationship. But others definitely do put numbers into this without understanding what this does. How it works is you cover up the quantity that is the subject of the equation. Speed equals, therefore we cover up speed, and it shows that distance divided by time gives the answer. Now, using it this way as a black box is an example of procedural teaching. To teach someone to use a procedure without understanding what that procedure is doing. It also takes away from the pupil opportunities to create a firm foundation on which to build and add further skills. So, for example, in this particular instance, I can rearrange 3 variable equations, but what I can't do is add anything onto that knowledge to help me rearrange equations with more than 3 variables, for example. Now, this is quite a famous example of procedural teaching. And of course, the opposite of this, the conceptual teaching, is to understand what the relationships actually mean. The power of per, for example, is a brilliant way of talking about the relationship that doesn't just straight away stick it into a formula. To understand that in dimensional analysis, that the meters per second is actually quite difficult, but though you can see it is related to this triangle and this formula and this relationship, that say 5 meters every second, and makes the student understand what that speed actually represents. And so what we've gone for in that route is an example of conceptual teaching, to understand for the understanding's sake. And so therefore it creates a more firm foundation on which to build further knowledge. Now, other such examples of conceptual and procedural teaching exist in physics. And one of the ones that I want to talk to you about are unit conversions. Now, we're all familiar with the idea that the units in physics can be prefixed with something like micro or milli or centi or kilo or mega, to make the unit 1,000 times bigger or 1,000 times smaller, whichever is the most relevant. But of course, this becomes more complicated when we look at things like area and volume, for example. So, say for example, I had a wire and it was 2 millimeters by 2 millimeters, and we're going to say for now that it's a square cross-sectional wire. It doesn't have to be, it could be a circular wire like most wires are. If I was to work out what the area of this wire's cross-section is, I would simply do 2 squared, which is equal to 4 millimeters squared. What I've done there is I've got the area in millimeters squared. Now, at this stage, what I could do is if I wanted that area in meters squared, then there is a procedure that allows me to do it really easily, and you do it all the time. In fact, nearly all professional physicists, mathematicians, general public do it. They probably just Google a conversion factor. Like, what do we need to do to convert millimeters squared into meters squared? And what you'll probably find is that what you need to do is divide by 1,000,000. And so you apply that and you get the answer. But that was a black box without understanding of how can something go from millimeters squared to meters squared that has a factor of 1,000 in it by dividing by 1,000,000? What I think is a better way of doing it is to explain conceptually what is going on. What I could do at this stage is to point out that if I converted both of these into meters, I would have to divide both of these by 1,000. It would be like 2 divided by 1,000 multiplied by 2 divided by 1,000. And so what we would get is 4 times 10 to the minus 6 meters squared. It is 1,000,000 times smaller. And that is because not only have we multiplied the 2's together, but we've also then divided it by 1,000 times 1,000, by 1,000,000. We've divided it by 1,000. So that's one way of getting towards a conceptual understanding of why would it be 1,000,000 times smaller. Part of the thing with conceptual teaching is that it promises to give us a firm foundation on which to build higher order and higher level structures on which we can build further knowledge. So is there a way of now advancing this particular piece of understanding to build further things on it? If not, then it's pointless and we might as well use the procedure. But if so, then there's value in explicitly teaching these sorts of dimensional analysis at an early stage. Now consider this. Consider that instead of being given a cross-section where the dimensions, the length and the width are known, or if it was a circle, say the diameter or the radius was known, imagine if we were just given a random shape. In this particular example, we'll give it just a circular shape, and what we're told about it is that the area is 5 millimeters squared. Now our issue here is that we cannot do this step. But what we know from this step is that this methodology works. And so what I would say to pupils is rather than just blankly now dividing that by 1,000,000, is to consider an approach that is understood that would get you the same answer. So basically, it's taking away the hidden workings of the black box. And so this is what I'd tell them to do. Now this circle could be represented as a square of the same area. So that's 5 millimeters squared as well. And one of the things I've done up here is to convert it into meters squared. I've first converted these side lengths from millimeters into meters. But the thing is, I don't know what the side lengths are here. But if I model it as a square, then I could work out the side lengths and convert those into meters. So the first thing I would do is I would take the area, and this is the area in millimeters squared, and I would want to know what the side lengths were would be of an area of this magnitude if we modelled it on a square. So what I would do is I would take the square root of that answer, and that would essentially give me the side lengths of this and this. There would be root 5 at each one of them. But then I'd want to convert those into meters squared. So the very next step is I would have to divide that by 1,000. That would tell me what these two would be. But to work out the area in meters squared, I need to now multiply that side length and that side length. And so what I need to do is take this whole formula and square it. And this would give me my area in meters squared. Now, the power of this particular formula is it is actually applicable when you slightly adjust it to lots of situations. For example, the area in centimeters squared, square rooted, divided in this case not by 1,000, because we're going from centi to a metre. We're going to divide by 100 because there are 100 centimetres in a metre, and then square it. This gives us our area in metres squared from centimetres squared, a useful conversion. And though we don't often do it the other way around, just a simple rearrangement of this formula would enable us to get back again from metres squared into millimetres squared, if that was ever a thing. Furthermore, this method is so powerful that what we could do is with the volume in, for example, millimeters cubed, if we cube rooted it to find what all three important sides magnitude of length was, and then divided that by 1,000, and then cube that, you would get the volume back in meters cubed, and divide by 100 to get it from centimeters cubed back to meters cubed. So here, what we have is we have developed a conceptual understanding of what the conversion is doing. We take away the black box. It took, in this video, perhaps 5 minutes to explain, but what it has meant is that I've now come to a point where I could apply this method again and again in situations of any complexity. Not only that, you can see that this method enables us to spot very similar examples that could use the same approach, and therefore we would never have to remember a unit conversion ever again. And so this concludes this video. I hope you found it useful. Please like and subscribe to my channel.